Welcome to Highline BI 348 class video number 57. Hey, if you want to download this PowerPoint file and follow along, click on the link below the video. Hey, we're in chapter 8 and 9, which is an introduction to linear programming. Let's go to our topic slide. Next slide. We're going to have in this video an introduction to linear programming, talk about the objective function, the constraint functions, and we're going to have more fun than you thought possible with linear algebra. And we'll use linear algebra to create a solution for a two decision variables, a manufacturing problem where we're trying to maximize contribution margin. Now we got to do the linear algebra and the graphing part before we can get to our Excel solutions for linear programming to find optimal solutions. It will help us to understand what Excel is doing behind the scenes. Now let's go to slide number 4. Linear programming. What is linear programming? It's also called linear optimization. Linear programming, using linear algebra to either maximize or minimize the objective function given a set of constraints. Now, the objective function is something like, hey, total profit, and we're trying to maximize. Constraints are things like, hey, there's these demand constraints that we have to take into consideration. Now, in either case, whether we're using algebra or we're using Excel, we're going to have to build a mathematical model built with linear equations for the objective function and the constraints. So really, the reason that we're starting using linear algebra is because it really is a lot of math. And if you don't understand the math behind it, then it's hard to even set up over in Excel. And here's our example. We're going to have a computer manufacturing company who wants to maximize contribution margin, that's a type of profit, from the sales of 2 laptop computers given the following facts. Laptop 1 price is $295, the cost is $200. Laptop 2 price is $450, the cost of goods sold is $400. We have some constraints. The maximum we're allowed for this project on cost of goods sold is $700,000. The maximum estimated demand for laptop 1 is $200, and the minimum demand for laptop 1 is $100. And we will see how to do this exact example in this video with linear algebra and the next video with Excel solver feature. Now, next slide, we've got to talk about steps in building a linear program. Read problem carefully and take notes, or if you're out there in the working world, you got to gather up all the necessary data. This sometimes takes a long time. Some of the homework problems in our textbook, they're big, huge problems. You're going to have to really read them carefully. I always take notes as I'm reading the problems. Then we're going to list the variables and state objective. State objective either to maximize or minimize some function. Define decision variables. Decision variables are variables that managers have control over. List all the parameters, assumptions, formula, inputs, and coefficients. That just means the number in front of the decision variable. List the constraints. Then we have to, number 3, define our linear equations. The objective function, that's the function to minimize or maximize. And then we have to define linear equations for our constraint functions. These are formulas that place limitations on finding an optimal solution, like the maximum for cost of goods sold equals $700,000. We will see in this video how to solve on paper using algebra. Next video, we will see Excel solver. Now here's the complete description of our problem. A computer company plans to sell 2 versions of a laptop, laptop 1 and laptop 2, at a price of $295 and $450 respectively, with a cost of goods sold of $250 and $400. Our first constraint, the maximum monthly demand for laptop 1 is 200 units. The min monthly demand for laptop 2 is 100 units, so that reflects the fact that we've already signed a particular contract, so we have to have a min of that one. Total cost of goods sold should not exceed $700,000. And our objective or goal What number of units will maximize contribution margin? Now that is what we will try to solve using linear algebra or Excel solver. Now contribution margin is simply sales minus cost of goods sold. It means the amount left over that can contribute to other expenses besides cost of goods sold and profit. We're going to have to list our goal, all the variables including the decision variable, and the decision variable for us will be number of units sold, the objective function, the constraints which will be listed as constraint functions, and we'll solve this using linear algebra and Excel solver. Now why are we using linear algebra instead of jumping straight into Excel solver? Because the linear algebra part of it, and in particular the graphing, will help us understand why all of this makes sense and the meaning of it. Then we'll jump over and see how to use Excel. And in particular, Excel will help us solve larger problems when we have many decision variables. Now, step 1, list variables, which will be our formula inputs, decision variables, and facts. All right, so I made a little grid here. There's product 1 and product 2. Our price for laptop number 1, $295, and our price for laptop 2 will be $450. Cost of goods sold will be $250 here and $400 here. Now these are per unit, so when we calculate contribution margin, price minus cost of goods sold, that'll be per unit. So this one will be $45 and this one will be $50. Now very important for all of our linear algebra problems, we'll have to define the decision variable, and so this will be number of units, and I'm going to call this one X and Y. Now in the book they call them S and D or X sub 1, X sub 2, but for our first example when we're going to plot it, I'll just use X and Y. Now very important, this is our decision variable. This will be on the X and Y axis. The intersection of all of our lines will give us the optimal solution. When we get over to Excel solver, this decision variable is what we'll tell solver to look at to try and find the optimal solution. Now for our example here, right, if the optimal solution was 10 units of this and 10 units of this, which wouldn't meet one of our constraints, but I can do that math in my head. It would mean we'll have 10 and 10. Those would be the optimal solutions. It would be 10 times 45 would be $450, and 10 times 500 would be $500, so it would be $950 would be the maximum profit. All right, so that's the decision variable. Now, although we could jump straight to our objective function and our constraint functions, meaning the math equations, right? I like to write them both out. That way I'm clear before I start doing all the math or the Excel about what my goal is and what the constraints are. Max total demand for laptop 1 is 200. Now later we'll have to make a math equation out of this, and that 200 will be the upper limit. Another constraint, the min total demand for laptop 2 is 100. And when we make our constraint function or formula, that will be the lower limit. Our next written constraint, the maximum total cost of goods sold is $700,000. Again, so when we do our math formulas and our Excel formulas, that will be the max amount. Written objective or goal, hey, we're going to maximize contribution margin. So when we do our math, we'll have a formula to calculate the total contribution margin, and when we get over to Excel, we'll also have a formula. Now let's go to our next page. All right, now we're going to have to build our math model, which means we'll have to list our objective function and then our constraint functions. So we'll start with objective function. So the objective function is what we're going to try and maximize. So we're going to start out with $45 of contribution margin, and I need to multiply that times the number of units for laptop 1 plus the contribution margin $50 for laptop 2 times the number of units for laptop 2. That will equal total contribution margin, and we'll abbreviate that with TCM for total contribution margin. All right, now we have to list our constraint functions. Now remember, we have max unit of 200, min of 100, and max cost of goods sold is 700 and 1,000. Those ones are obvious. That's from our written description. But we got to think also the actual first and second constraints have to be, hey, we can't have minus units sold. There can be no negative units. So for our first equation, we're going to say, hey, x, the number of units for laptop 1, you have to be greater than or equal to 0. This is called a non-negativity constraint. Well, of course, we have to have a similar equation, but for y greater than or equal to 0. And that'll also be a non-negativity constraint. Now, equation number 3, we have to think about the number of units for laptop 1. And remember, there was an upper limit. The max demand is 200 units. So x can go all the way up to, but not exceed 200. So x has to be less than or equal to 200. So you see with these two, x will be somewhere between 0 and 200. Our fourth equation is for number of units for laptop 2, and that has a min amount. We have a contract already signed, guaranteed we have to ship 100. So in this case, the smallest y can be is 100. So y can be bigger than or equal to 100. And then finally we have equation number 5, and I'm going to put this out here. I was going to try and line up all of the comparative operators, but I don't think I'm going to be able to do that. Remember, we have 700,000 as the max cost of goods sold. Well, how much is cost of goods sold for one X unit, laptop 1? 250 bucks. So I say 250 times the number of units sold for X plus 400 bucks. That's the cost of goods sold for 1 unit of Y times Y. And then the upper limit is 700,000. So the biggest that this can be is 700,000. So this can be less than or equal to. Now I didn't write, this is the max demand for X, and this is the min demand for Y. All 5, those are going to be the constraints that will limit the objective function. So when we do our linear algebra in graphing or Excel solver, this equation will try to be maximized given all of these constraints. Now there's something important the way I've arranged these. On the left is the actual function, and on the right is the actual constraint amount or limit. Now that's important that there's the left and the right. In the textbook and the way they describe it, and when we get over to Excel, it's all set up. The function is on the left and the constraint is on the right. So I'm going to write that out here. So the constraint functions will be on the left-hand side. I wrote that kind of wiggly, but the constraint limits are on the right-hand side. So again, as everything's described in the textbook, they refer to it as this. Not only that, but when our Excel solver dialog box and the answer report and sensitivity reports that are spit out all refer to this as the right-hand side. Now, all of these equations I can plot pretty easily. I'll put 2 points to define a line for each one of these. But this one I want to actually solve for y. So I'm going to start off, I'm going to say subtract minus 250x from both sides, so that would leave that with 0. On this side of the inequality, I'm left with 400y less than or equal to, and on this side I have minus 250x plus our 700,000. Now I'm going to divide both sides by 400, so here I'm left with y less than or equal to minus 250 divided by 400x plus 700,000 divided by 400. And I think we can get y less than or equal to, and I'm going to reduce this by sliding the decimal in the numerator and the denominator, so I get minus 2.5 divided by 4x plus, and if I do this in my head, no, I already did it in Excel, I get 175. So now that equation right there we can plot. Let's go to our next page. All right, here's where we are going to plot our inequalities. Here is the x-axis. X is number of units produced and sold for laptop number 1. The y-axis is along there. Y, number of units produced and sold for laptop number 2. We're going to use increments of 25 all the way up to 300. Increments of 25 all the way up to 300. Now, I've already plotted equation number 1. That looks like the y-axis, right? But it's really a plot of x greater than or equal to 0. Any value above can be our x, at least in terms of this first constraint. And because it's an inequality, I'm actually going to draw a line right like this. I'm going to draw this arrow just like that to indicate that it's everything that direction. And when we have all of our lines plotted, the arrows will point towards what's called the feasible region. Now, equation number 2 is actually not totally necessary, but I'm going to put it anyway. It's going to be equation number 2 is y is greater than or equal to 0. And it will look something like this. And we will have an arrow pointing up. Right? So that's our second equation. So right now you can see we have a black arrow and a red arrow pushing up this way. That means whatever answer has to be up in this area. I'm actually going to draw a line here because we're going to have to figure out some points for the rest of our equations or inequalities. Well, for 3, x less than or equal to 200. Well, really, if it was x equals to 200, there'd just be a line, because at any y value, x is going to be 200. So I'm going to use the points. Remember, x is 200 everywhere, so I'm going to choose a y of 0. And I'm going to choose, hey, x again is 200, and say a y value of 300. So it would be a point right there and a point right there. And so our equation, or inequality, will look something like this. And I'm going to put 3x has to be less than or equal to 200. Now equation number 4 is y, and this was a min, so it's y has to be greater than or equal to 100. Now again, that's why we don't need this red line here, because y, if y is 100 at every single x, then it's a horizontal line. I don't really need to have points here, but I'll put the points. Hey, 0 and 100, doesn't matter what x you throw in. I'm going to throw in a 300. I still get y equal to 100. So and if I were to plot this, it would look something like this. And so this will be 4. Y has to be greater than or equal to 100. Now I forgot the arrow, because remember, we're trying to get to some interior region that will define the feasible region for our maximum optimal solution. So we have an arrow that way, and then for our y greater than or equal to 100, we have an upward pointing arrow. Now I'm going to have to scoot this just a little bit down here so we can see the bottom here. Well, we only need 2 points, and we know that whatever that equation will be, it's going to a point on the y and x-axis is fine. So I could start off by saying, hey, I'm going to try and see what I can get if I plug x equals 0 into this. So that would get rid of that whole term. So y less than or equal to 175. So one of the points will be x equals 0 and y equals 175. Now let's see what will happen if I say y equals to 0. Well, over here, so I'm going to put 0 less than or equal to minus 2.5 over 4x plus 175. I can add 2.5 divided by 4x to both sides, so I'd get 2.5 divided by 4x less than or equal to 175. I want to take the inverse of this and multiply it by both sides. So I get x less than or equal to 4 over 2.5 times 175. And so I would get x less than or equal to 4 divided by 2.5 times 175. And that would give me x less than or equal to, I could have done equal signs throughout this, 280. Of course, I did that in my head. Now I went over to Excel and did it. So then we have our second point of x equals 280, y 0. 0x 175 y, that's 1 point. 280 is maybe right there with a y equal to 0. And I think I'm going to take a ruler and see if I can draw this line, this inequality. I'm going to use a green pen here. So equation 5 will be y less than or equal to minus 2.5. So the slope is minus 2.5 divided by 4. X plus 175, that's the y-intercept. And we come over here and we draw our arrow, and lo and behold, we have encircled or contained a region. And that region is called our magic feasible region. And the vertices, or the extreme points, are the x and y values we can plug into our objective function to actually determine the optimal solution. Now, technically, any x and y in this region right here meet the constraints set. But it happens to turn out that the vertices, or the extreme points, will be, if we plug them in, the x and y's, and figure out which one of these three values is the maximum, that will give us our optimal solution. Now I'm going to scoot this down here, and we're going to try, and we're going to say TCM, total contribution margin. And I'm going to use this point right here, 0, 175. And then the objective function, 45x plus 50y. So when we plug this in, we get 0 plus 50 times 175, and that will equal 8,750. Now it looks like we have 0, 100, so TCM 0, 100, and we already know this one's going to be less. So that will equal 5,000. Now the question remains, what are the coordinates there? And I'm not quite sure. So I'm going to take this inequality or equation and set it equal to that one and solve for x. So I'm going to say this is y equals to 100, or inequality. And then we have the second equation that is intersecting, y less than or equal to slope x plus 175. Now, y and y, I just set them equal to each other. So 100 goes there, and then all of this. So let's see. I'm going to take minus 100 on both sides. So if I subtract 100 from both sides, I'd be left with 75. And I'm going to add this entire term to this side and that side. So I get 2.5 divided by 4x. Now I want to solve for x, so I take the inverse of this, multiply it by both sides, and I get 4 divided by 2.5 times 75, and that will equal 120. So we have our 2 points, 100 and 120. So I'm going to do this right here. TCM 120, 100, and that will equal 45 times 120 plus 50 times 100, and that will equal 10,400. You got to be kidding me. So there it is. That intersection gives us the coordinates x equals 120. That means we produce 120 laptop 1, and y equals 100. We produce 100 laptop 2, and we get the maximum profit of 10,400. I'm even going to try and write that right here. So max profit 120, 100 equals 10,400. And that's going to be at that point right there. And if we look at our last page here, the feasible region defined by the vertices, the extreme points right there, that's our feasible regions. And we check 1, 2, 3, in our case 3 vertices or extreme points, and figure out which x and y gives us the maximum. Or later we'll have functions that we'll have objective functions where we'll have to minimize. Now when we get over to Excel, there's an algorithm called the simplex LP algorithm, which doesn't check everything, it just checks the vertices. All right, so when we're solving a problem like this, we want to be sure and define all of our variables, including our decision variable, understand our constraints and our goal. Then we want to make sure and write all of our functions, including the objective functions and all the constraint functions. Now notice this is all math. We have to do all of this over in Excel also, but they will be Excel formulas. And then finally, over in Excel, we will not have to do the graphing part and then finding the vertices and plugging them in to figure out which one is the maximum or minimum. We will click the solve button and it will do all of this for us and tell us exactly that coordinates 120 and 100 will yield the maximum profits. All right, in our next video, we'll see how to do this in Excel. We'll see you next video.